In this video, we're going to look at an introduction to a technique on how to solve second-order differential equations. Okay, at this point, we should already know the complementary function, particular integral method, from first order, and then this is just like an extension of that technique. The way it does get a little bit more awkward, obviously with it being a second-order differential equation, is that when you find your complementary function, so when we set it equal to 0 for the reduced equation, we're going to end up with a quadratic. Whereas before we just got one exponential function, we're going to get two separate exponential functions. And obviously with the quadratic, there's three things that can happen. You can have two real roots, you can have one repeated root, and you can have complex roots. So there's going to be different types of complementary functions that we could end up with. And you will need to remember these. You do not get given these in the exam. So there's a lot of practice that we're going to be doing in this booklet. And you know, once you've done a few of them, it's not as bad as it seems the first few times. But just stay with me. And we'll see how to solve using this technique. Particular integral is the same. You just look at what's on the right hand side, and obviously you've got to be careful because you've got to figure out your complementary function first. Okay, so we've got second order differential equation. It's just find the general solution. I'm going to start by saying let y equal. We know it's going to be an exponential for the complementary function, so a e to the mx. I think I used k in the last video. I'm going to use m. It doesn't matter what letter we use. Let y equal a e to the mx. Okay, and we're solving d2 y by the x squared minus 4 dy by the x plus 4y equals 0. I might show you where this comes from. Again, you don't need to. In the next example, we'll just skip to the way you set it out in the exam. But remember, the derivative of this would be, we'd multiply by this coefficient, so it'd be am e to the mx, and the second derivative, d2y by the x squared. If we differentiate this again, remember they're both constants, so we're only differentiating the exponential function. We multiply by m again, and that would be a m squared e to the mx. So once we've realised that we know it's going to be an exponential of this form, and we find its derivatives and we sub it in, we get a m squared e to the mx minus 4a m e to the mx plus 4a e to the mx, and then we can take a common factor out of a e to the mx, and we are left with m squared minus 4m plus 4. Clearly the exponential function doesn't equal 0, and we solve the quadratic. Okay, this little bit of working out here we don't need to show in the exam, unless maybe there might be a weird question where it specifically says show, but I don't think they would ask that because this is normally just the first 1 or 2 marks on like a 10-mark question. So as long as we know it's going to be an exponential function, you can literally skip straight to these coefficients of our derivative of our differential equation, give us our coefficients of our quadratic. Okay, so that would be m squared minus 4m plus 4. Don't mess this step up, alright? I don't want to patronise you, but make sure you solve your quadratic properly. Literally, this is like a 10-mark question, and I've seen people make a mistake on the quadratic at the beginning, and you just get into a complete mess. Like, we've got to be very careful in the way that we approach these questions. You've got to set your work out neatly. You've also got to be very thorough in each step, because if you rush and you make a little mistake, you end up having a knock-on effect and it takes you much more time. So just try and get that balance between working efficiently but also working accurately. It's really important on this topic. This is a repeated root, isn't it? M minus 2 squared, so m equals 2. So if we get a repeated root, I know that my complementary function would be a plus bx e to the 2x. So another way of thinking about that, right, is if you think about a repeated root, you've got 2 and you've got 2. So then you'd say, well, I know if I get my solution is 2, I know I'm going to need some e to the 2x's. Remember, because we just know that this complementary function is going to be this form, a e to the mx, and all we're doing is figuring out what m is. So once we've got m as 2, we say, oh, I need some e to the 2x's. And then if it was 2 again, you might say, oh, I need some more e to the 2x's, but that's nonsense because that would just be e to the 2x's. So it's it's almost like the case where we had the particular integral. You've got some e to the 2x's, but you've also got some x, e to the 2x's. Okay, and that's what this form is. So once we've got our complementary function, we need to figure out our particular integral. Let's have a look at what's on the right hand side. Here we've got a polynomial. Obviously we don't have any exponentials, so we don't need to worry about any unusual particular integrals. So for the particular integral, I'm going to let y equal, well, be careful, we've got a and b already, so we'll need to c, we need some x's, and we need the constants. Okay, and just the same as the first order, once you've realised what your particular integral is, you just differentiate it and sub it in. So the derivative, I'm just going to write it as y dash, you can write dy by dx if you want, it would be c, and the second derivative would be 0. So once we sub into our differential equation, we would get 0 minus 4c plus 4 cx plus d, and that's equal to 12x minus 8. And then we just use the same technique, we'll just equate coefficients on both sides. So if I compare the x terms, possibly expand this out, again you want to be a little bit careful, you don't want to make any mistakes at this point, but we'd have 4c x's on the left and 12 on the right. If we equate the constants, x to the power 0 is a constant, we've got minus 4c plus 4d, and that would equal minus 8. Okay, just check, minus 4c plus 4d. Okay, so we know c equals 3, sub that in, minus 12 plus 4d equals minus 8. Add 12 to both sides, we get d equals 1. Okay, so we just have to find the general solution. We've got our complementary function. We've figured out our particular integral. So at this point I would write therefore y would equal a plus bx e to the 2x plus c, which is 3, plus d, which is 1. And obviously we might look a bit later getting some particular solution, not just a general solution. Now we've got two constants to find, so if we do ever want to get the full particular solution, we'd have to be given two pieces of information. One coordinate wouldn't be enough, we'd need two things to work with. Okay, let's try the next one. Okay, next example, we are going to find the particular solution. So we've been given a second order differential equation, and we've got two pieces of information, which is going to enable us to find the constants. Let's first of all get the complementary function. Okay, so for the CF, I'm going to say like y equal a e to the mx. We're solving it equal to 0, so then we'd get m squared plus 2m plus 10 equals 0. So I think this is going to give us complex roots just from looking at it. I'm trying to factorize it in my head. It doesn't factorize. If you do a quick calculation, b squared minus 4ac, it's going to get negative roots. Okay, so the best way to solve, if we're going to get complex roots, obviously you can use a graphical calculator as long as you're set up in complex mode. But the method I would always approach with this is completing the square, because I think that's the quickest way. You can use the quadratic formula as well if you want, but if we complete the square, the answer comes really quickly. So that'll be m plus 1 all squared, subtract 1, so that'll be plus 9. M plus 1 squared equals minus 9. Square root plus or minus, square root of minus 9 would be 3i, and then m would equal minus 1 plus or minus 3i. Okay, so when we get complex roots, that's the one that maybe takes the most time to get your head around. There is a proof of where this comes from. I'm definitely not going to go through it now, but you have a look in the booklet for the proof. Okay, you don't need to know the proof in the exam. All right. So the real coefficient is the exponential power. The imaginary coefficient is now the coefficients inside your sine and cos. Okay, so I'm going to write my complementary function would be e to the minus x a cos 3x and b sine 3x. So obviously we'll have to find these coefficients to get our full particular solution. Okay, so let's see. We've got our complex function. Looking at the right hand side, we've got cos x and sine x terms. So for the particular integral, I'm going to let y equal, now again we've got a and b already, so I'm going to say c cos x and d sine x. There is a guide on particular integrals in the booklet, and remember, essentially with your particular integral, you're looking at the right hand side and we're saying, well, there's a function, there's its derivative and its second derivative, and combinations of this function end up being cos x and sine x, and you know if you differentiate sine x you get cos x, if you differentiate cos x you get minus sine x. So my particular integral has to be coses and sines, because that's what satisfies this differential equation. Okay, I'm going to write this. We should be good at this by now, but it's nice for reference. You get your derivative, so that would become minus d sine x plus, it wouldn't, it become minus c sine x plus d cos x, and the second derivative would become minus c cos x minus d sine x. We're going to have to be careful how we set this out. I might run out of space on this mini whiteboard, but you've got to sub this into your second derivative, into your full differential equation, okay? So that become minus c cos x minus d sine x plus 2 minus c sine x plus d cos x plus 10 c cos x plus d sine x, and that is equivalent to 13 cos x plus 16 sine x. Okay, looks a bit messy this, but let's equate coefficients. Just be careful as we do it. If we equate the sine x terms, you probably want to highlight this as you go because there's a fair amount going on. You've got minus d minus 2c and 10d, and that's equal to 16. For the cos, we've got minus c two d and 10c, and that is equal to 13. Okay, so we'll just solve these simultaneously. If you need to, you can use your graphical calculator and you go onto gsolve, so the menu equation, but obviously it's just a linear set of simultaneous equations. Is there a quick way of us doing it? Oops, we'd have 2d plus 9c equals 13 and minus 2c plus 9d equals 16. No, not really. I suppose we could multiply and then subtract or add. I'm just going to pause it 1 sec while I solve these, save me doing that because I know you can do that bit. You know, actually thinking about it, because in the exam you won't need to show a method, save you wasting time on this, because they are pretty awkward as it comes, because if you do try and rearrange to make them on the subject, you will get fractions, and obviously if you want to multiply, you have to multiply by 18. So the way to do it on the graphical calculator, go on to equation, and then simultaneous, so F1, number of unknowns, we've got 2 unknowns. Now you have to be careful when you type this in because it's ax plus by equals c, so I would technically have to write that in the same form, so that would be 9, why none of my pens working, 9c plus 2d, just so you've got the c represents x, the d represents y, and then enter your coefficients, so 9, 2 equals 13, minus 2, 9 equals 16, solve, okay, so we end up with x equals 1, so therefore c equals 1, and d equals 2. Once we've done that, and we've found our particular integral, we found our complementary function, we've still got a little bit more work to do. So this would potentially be worth quite a lot of marks, this. I'm just going to tidy this up and then we'll look at how to find these constants. Okay, so you might not have actually seen this notation before. I'm not sure if it's in the AS. It says y of 0 is equal to 1. The thing inside that you're subbing in is the x value, so that's basically telling me when x equals 0. We know that y equals 1, and this thing is the derivative, y prime is the derivative, so if I sub 0 in, so if x equals 0, I know two things. I know when x equals 0, and on this original curve, I know the y value is 1, but I also know that when x equals 0, I know that the gradient is equal to 8. And a couple of people make mistakes with that information if that's given to you, because if you're told the derivative is equal to 8, you actually have to use this full general solution and differentiate it, and it's going to take a bit of time to do this, okay? Don't start going back and looking at derivatives earlier on, and like just a particular integral or just a complementary function. You need to use the full general solution to use this information, okay? And this is our, don't forget, this is our full general solution here. So you have to refer back to this to find the constants. Let's do x is 0, y is 1, so 1, e to the 0 would be 1, cos of 0 is 1, sine of 0 is 0, cos of 0 is 1, sine of 0 is 0, so what do we end up with? 1 times a plus 1. Oh, that's nice actually, because I think we end up with a equals 0, and as soon as I know that, that's going to make this next step a little bit quicker. So a is 0, now we can just figure out what b is, okay? So the way that we're going to have to do this, you need to use the fact that dy by dx is equal to 8, so we have to differentiate this full function, and we are going to be using the product rule with this term. We don't have to worry about that one anymore. So dy by dx would be e to the minus x, and then differentiate this, so that would become 3b cos 3x plus, differentiate this one, I'm just using the product rule here, minus e to the minus x, b sine 3x, cos would become minus sine x plus 2 cos x. Okay, so this is the equation that I can use. This x equals 0, we know dy by dx is equal to 8. E to the 0 would be 1. Cos of 0 is 1. E to the 0 is 1. Sine of 0 is 0. Sine of 0 is 0. Cos of 0 is 1. Okay, so we would get b equals 2, just from solving that, 6 divided by 3. Okay, so we're done. Right, we found our coefficients, we've got our general solution, so our particular solution therefore would be y would equal e to the minus x. I actually could write this in a different way, because normally we'd put it in a bracket, but because a is 0, inside that bracket we've got 2 sine 3x's, so I could bring the 2 to the front, so it'd be 2 e to the minus x sine 3x plus cos x plus 2 sine x. And if you really wanted to, you could differentiate this twice, sub it back in and check that it satisfies this differential equation. In the exam, you probably won't have time to do that, but if you want, as while you're still getting used to this topic, you could do that. Okay, what time are we on? Right, I'm going to stop the video there, and then I think we will need another video for the next couple of examples, because there's a few different cases that we've not seen yet. So there'll be one more video, guys, with 2 more examples. And then you've got a ton of questions to practice. This technique does take practice, so you can't just like watch me doing it and think, yeah, I'm all right with that. Until you sit down and do this and set the work out, you're not going to be able to reproduce it in an exam situation. So please give yourself enough time to practice these questions.